Hello guys, good morning. So today we will be solving a problem on effective length factor K using the AISC alignment chart and the British equation to compare to the theoretical values uh, of this table as recommended by uh, the AISC. So for the first step, we need to calculate the relative stiffness of the ends of the columns. Okay. So this is the formula for the relative stiffness psi, which is simply the ratio of the column stiffness all over the stiffness of the beam upon which your beam stiffness is represented by the joint stiffness. So imagine these support conditions are considered beam stiffness upon which the rotation of your ends is space. So for the relative stiffness of a pin joint, okay. So if we have a joint comprising a pin support, the stiffness of such joint is equivalent to a beam which has a very small stiffness ratio such that your EI over L for this beam here and this beam on the other side is considered to be 0. So if we take the uh, relative stiffness now of a pin joint, then we can say that any value which represent stiffness of the column divided by a very small value which represents the stiffness of the beam will yield to a very big value for your relative stiffness. So I assume a very small value here, since if I divide 1 uh, by 0, I will get an infinite number. So the small value here represents a value of the beam stiffness approaching 0. Hence, the psi of the pin is now a big value which represents an almost infinite value. So for your fixed joint, the relative stiffness EI may be represented by, again, a beam in which your EI over L is a very big number close to infinity, such that if I divide a value, say 1, which represents the stiffness of the column, by a number which is representing an infinite value, or rather a very big number, say 10,000, the value of the relative stiffness at the fixed joint will therefore be a very small value which can be approximated to a value of 0. So in summary, the psi, or the relative stiffness of a pin joint, is therefore a very big value, while the relative stiffness of a fixed joint represents a very small value which can be taken as 0. So for the next procedure, we tabulate the 6 cases using this table, noting that we have to consider if the brace or the columns are braced against lateral translation or not braced against lateral translation. Hence, for case 1 to 2, the 2 cases are therefore brace cases, since there are no lateral translation or side sway at any of the joints, while case 3 is an brace frame, since at the top joint the column is allowed to translate laterally at a certain distance delta. For case number 4, this is again a brace column, since there are no lateral translation at the ends of the column. For case 5, this is again an brace column. Also case 6, an brace column, since there are lateral translation delta at the top joints. So we also tabulated the theoretical K value and the recommended design value for K, which are here on this table. So the psi of the individual columns are also tabulated. For case 1, this is a fixed case. So we have 0, 0, assure psi 1 and psi 2. For case 2, we have a fixed spin. So this is a 0 infinity value. So we can see here 0 big or 0 infinity. And for case 3, we have 0, 0. This is fixed again, but with lateral translation. For case 4, we have pin with no lateral translation. And for case 5 and 6 are 0 infinity or fixed pin and pin fix with lateral translation. So simply by using the nomograph, we can say that the red line here represents your case 1, then this represents your case 2, the green here represents your case 3, Okay, so we might as well use the color to represent the case number. Okay, so this is now uh, the violet color, which represents case 2. We have the green color representing case 3, the blue color representing case 4, the orange color representing case 5, and purple color representing case 6. Okay, so for case 1, we simply plot the psi values of the two ends 0, 0. So we get k is simply equal to 0.50, which is then tabulated here in the nomograph column. Then for case 2, we plot the psi 0, infinity, so we get 0.7. Okay, as your value, which is then tabulated here. And then for case 3, it's again 0, 0, but this time it is plotted on the sway frame nomograph chart. So equivalent to 1.0. And for case 4, it's infinity, infinity, equivalent to 1.0. For case 5, it's 0, infinity again. On the sway frame graph, it's 2.0 and infinity 0, which is simply the reverse of case 5. We get k equals 2.0. So these are now the values of your k using the nomograph. For the equation, for the values using the equation, we have case 1. Okay, so for case 1, we simply go into the formula upon which your k1 and k2 here are two options from where the minimum value of k will be obtained, representing the final value of k. So it's 0.70 times 0.05, the sum of the two sides. Okay, for this particular case, this is now psi 0, 0. So if these are 0, then simply this will become 0.70 and 0.85. We choose the minimum value and it will come up with 0.7 as your value for k using the equation as tabulated on the table. For case 2, we have a brace frame again. So this is again the formula to be used. And by this time, we have a very big value for k1 since we only get the sum of the two values in which one of the sides involves a very big number, infinity. Hence, the value of k will be determined by the second formula, upon which we only take the minimum value for psi of the 0. Okay, the value of psi, which is 0 here as reflected on the table. So this is now 0 times 0.05, so it becomes 0. So we get now a value equivalent to 0.85. So this will now be equal to 0.85. So you take the minimum of the two, then finally your K becomes 0.85 as tabulated on the table. For case 3, 4, 5, and 6, we have values of psi involving 0, 0, infinity, infinity, and 0, infinity, infinity, 0. So we're in the cases 3, 5, and 6 are actually unbraced. Okay, so case 3, 5, and 6 will be having the same formula, different from the formula we have on the first two cases. So this is now a psi mean. We take the mean of the two, which is actually 0. Then we get the value of k on basis of this formula. So we then consider k becoming equal to 1. Take note that this formula is only valid if, okay, this condition is satisfied. Okay, for case 4 scenario, which is also an unbraced scenario, okay, so case 4, sorry, it's a brace condition. We again copy the formula of case 1 and case 2 such that we only take the minimum of the two options involved for determining K1 and K2. Okay, so we get the minimum, but since the minimum are also very big numbers, we then apply the limitation such that your K for brace frame must not exceed, okay, 1.0. But since this is bigger than 1.0, then automatically your K is plugged to be equivalent to 1. So take note that for brace frame, always your K must not, okay, be equal, sorry, must not be greater than 1.0. So for case 5 and 6, which are again unbraced conditions, we just take the formula for case 3. We take the mean or the average for the psi 1s and psi 2s. And we take note that since this exceeds again a value greater than 3, okay, we cannot use the formula on case 3, but rather use another formula wherein it captures the condition where there is a pinned, okay, a pinned condition or as shown here in your 5 and 6. Okay, so this has a pinned condition at the top and the pinned condition at the bottom. So we now use another formula for 5, 6, which is 2 plus 0.30 of the psi of the pinned condition. And of course, the pinned condition the psi here actually refers to the minimum value of the psi in either cases. So what is the psi for a pin condition? As shown here, it is a very big value, but for fixed condition, it's a very small value. So we use the value of 0 to represent, okay, to represent the value of psi here. Okay, so this is now the minimum value, which is equivalent to 0. So this cancels, and therefore your k simply becomes 2, which is also same as that obtained in case 5. So the values of psi with large exponents simply means that a value close to infinity is represented by it. Okay, so for the summary as seen on this table, we can therefore compare the two methods upon which your case 3 to 6 are just the same, while case 1 and 2 here have some differences, which assumes that your nomograph actually accounts for theoretical values, while the British equation accounts for almost the design values as recommended by the AISC. So thank you very much for listening. Have a nice day, and I'll see you on the next video.